Mars versus Earth. The differences between Mars and Earth are all crucial for the existence of life as we know it. For instance, atmospheric pressure on Mars is a tiny fraction of what it is here on Earth, averaging 7.5 millibars on Mars to just over 1,000 here on Earth. The average surface temperature is also lower on Mars, ranking it at a frigid minus 63 Celsius compared to Earth's balmy 14 degrees Celsius. And while the length of a Martian day is roughly the same as it is here on Earth, 24 hours, 37 minutes, the length of a Martian year is significantly longer, 687 days. On top of that, the gravity on Mars' surface is much lower than it is here on Earth, 62% lower to be precise. At just 0.376 of the Earth's standard, or 0.376 grams, a person who weighs 100 kilograms on Earth would weigh only 38 kilograms on Mars. This difference in surface gravity is due to a number of factors: mass, density, and radius being the foremost. Even though Mars has almost the same land surface area as Earth, it only has half the diameter and less density than Earth, possessing roughly 15% of the Earth's volume and 11% of its mass. Calculating Martian gravity. Scientists have calculated Mars' gravity based on Newton's theory of universal gravitation, which states that the gravitational force exerted by an object is proportional to its mass. When applied to a spherical body like a planet with a given mass, the surface gravity will be approximately inversely proportional to the square of its radius. When applied to a spherical body with a given average density, it will be approximately proportional to its radius. For instance, Mars has a mass of 6.4171 times 1023 kilograms, which is 0.107 times the mass of Earth. It also has a mean radius of 3,389.5 kilometers, which works out to 0.532 Earth radius. The surface gravity of Mars can therefore be expressed mathematically as 0.107 by 0.532 squared, from which we get the value of 0.376. Based on the Earth's own surface gravity, this works out to an acceleration of 3.711 meters per second squared. At present, it's unknown what effects long-term exposure to this amount of gravity will have on the human body. However, ongoing research into the effects of microgravity on astronauts has shown that it has a detrimental effect on health, which includes loss of muscle mass, bone density, organ function, and even eyesight. Understanding Mars' gravity and its effect on terrestrial beings is an important first step if we want to send astronauts, explorers, and even settlers there someday. Basically, the effects of long-term exposure to gravity that is just over one-third the Earth normal will be a key aspect of any plans for upcoming manned missions or colonization efforts. For example, crowdsourced projects like Mars One make allowances for the likelihood of muscle deterioration and osteoporosis for their participants. Citing a recent study of International Space Station astronauts, they acknowledge that mission durations ranging from 4 to 6 months show a maximum loss of 30% muscle performance and a maximum loss of 15% muscle mass. Their proposed mission calls for many months in space to get to Mars, and for those volunteering to spend the rest of their lives living on the Martian surface. Naturally, they also claim that their astronauts will be well prepared with scientifically valid countermeasures program that will keep them healthy, not only for the mission to Mars, but also as they become adjusted to life under gravity on the Mars surface. What these measures are remains to be seen. Learning more about Martian gravity and how terrestrial organisms fare under it could be a boon for space exploration and missions to other planets as well. And as more information is produced by the many robotic lander and orbiter missions on Mars, as well as planned manned missions, we can expect to get a clearer picture of what Martian gravity is like up close. As we get closer to NASA's proposed manned mission to Mars, which is currently scheduled to take place in 2030, we can certainly expect that more research efforts will be attempted. The epic journey to Mars. If you wanted to pay a visit to the Red Planet, how long would it take? The answer depends on several things, ranging from the position of the planets to the technology that would propel you there. Let's examine a few of the most important points. How far away is Mars? To determine how long it will take to reach Mars, we must first know the distance between the two planets. Mars is the fourth planet from the Sun and the second closest to Earth. Venus is the closest. But the distance between the two planets is constantly changing as they travel around the Sun. In theory, the closest that Earth and Mars would approach each other would be when Mars is at its closest point to the Sun, and Earth is at its farthest. This would put the planets only 33.9 million miles, 54.6 million kilometers apart. However, this has never happened in recorded history. The closest recorded approach of the two planets occurred in 2003, when they were only 34.8 million miles apart, 56 million kilometers. The two planets are furthest apart when they're both at their furthest from the Sun on opposite sides of the star. At this point, they can be 250 million miles, 401 million kilometers apart. The average distance between the two planets is 140 million miles, 225 million kilometers. Of course, the problem with the previous calculations is that they measure distance between the two planets as a straight line. Traveling through the farthest passing of Earth and Mars would involve a trip directly through the Sun, while spacecraft must of necessity move in orbit around the solar system star. Although this isn't a problem for the closest approach when the planets are on the same side of the Sun, another problem exists. The numbers also assume that the two planets remain at a constant distance. That is, when a probe is launched from Earth while the two planets are at the closest approach, Mars would remain the same distance away over the course of the 39 days it took the probe to travel. Countdown, the boldest Mars missions in history. However, the planets are continuously moving in their orbits around the Sun. Engineers must calculate the ideal orbits for sending a spacecraft from Earth to Mars. Their numbers factor in not only distance, but also fuel efficiency. Like throwing a dart at a moving target, they must calculate where the planet will be when the spacecraft arrives, not where it is when it leaves Earth. Spaceships must also decelerate to enter orbit around a new planet to avoid overshooting it. How long it takes to reach Mars depends on where in their orbits the two planets lie when a mission is launched. It also depends on the technological developments of propulsion systems. According to NASA Goddard Space Flight Center's website, the ideal lineup for a launch to Mars would get you to the planet in roughly 9 months. The website quotes physics professor Craig C. Patton of the University of California, San Diego. It takes the Earth 1 year to orbit the Sun, and it takes Mars about 1.9 years, say 2 years for easy calculation, to orbit the Sun. The elliptical orbit, which carries you from Earth to Mars, is longer than Earth's orbit, but shorter than Mars' orbit. Accordingly, we can estimate the time it would take to complete this orbit by averaging the lengths of Earth's orbit and Mars's orbit. Therefore, it would take about 1.5 years to complete the elliptical orbit. In the 9 months it takes to get to Mars, Mars moves a considerable distance around in its orbit, about 3/8 of the way around the Sun. You have to plan ahead to make sure that by the time you reach the distance of Mars's orbit, that Mars is where you need it to be. Practically, this means that you can only begin your trip when Earth and Mars are properly lined up. This only happens every 26 months. That is, there's only one launch window every 26 months. The trip could be shortened by burning more fuel, a process not ideal with today's technology, Patton said. Evolving technology can help to shorten the flight. NASA's Space Launch System, SLS, will be the new workhorse for carrying upcoming missions and potentially humans to the Red Planet. SLS is currently being constructed and tested with its first flight planned in 2019. Robotic spacecraft could one day make the trip in only 3 days. Photon propulsion would rely on a powerful laser to accelerate spacecraft to velocities approaching the speed of light. Philip Lubin, a physics professor at the University of California, Santa Barbara, and his team are working on the directed energy propulsion for interstellar exploration, DEEP-IN. The method could propel a 220-pound, 100-kilogram robotic spacecraft to Mars in only 3 days, he said. There are recent advances which take this from science fiction to science reality, Lubin said at the 2015 NASA Innovative Advanced Concepts Fall Symposium. There is no known reason why we cannot do this. How long did it take? Here's a list of how long it took several historical missions to reach the Red Planet. Their launch dates are included for perspective. Mariner 4, the first spacecraft to go to Mars, 1965 flyby, 228 days. Mariner 6, 1969 flyby, 155 days. Mariner 7, 1969 flyby, 128 days. Mariner 9, the first spacecraft to orbit Mars, 1971, 168 days. Viking 1, the first U.S. craft to land on Mars, 1975, 304 days. Viking 2 orbiter lander, 1975, 333 days. Mars Global Surveyor, 1996, 308 days. Mars Pathfinder, 1996, 212 days. Mars Odyssey, 2001, 200 days. Mars Express Orbiter, 2003, 201 days. Mars Reconnaissance Orbiter, 2005, 210 days. Mars Science Laboratory, 2011, 254 days. Physical and mental health issues. In addition to the rough terrain, freezing temperatures, and dust storms, astronauts would also have to worry about the mental and physical health issues that could develop. The human body in space. What happens to your body in space? NASA's Human Research Program has been unfolding answers for over a decade. Space is a dangerous, unfriendly place, isolated from family and friends, exposed to radiation that could increase your lifetime risk for cancer, a diet high in freeze-dried food, require daily exercise to keep your muscles and bones from deteriorating, a carefully scripted, high-tempo work schedule, and confinement with 3 coworkers picked to travel with you by your boss. How space affects the human body. But what exactly happens to your body in space, and what are the risks? Are the risks the same for 6 months on the space station versus 3 years on a Mars mission? No. There are several risks NASA is researching for a Mars mission. The risks are grouped into 5 categories related to the stresses they place on the space traveler: gravity fields, isolation/confinement, hostile/closed environments, space radiation, and distance from Earth. Scott Kelly was the first American to spend nearly 1 year in space aboard the International Space Station, twice the normal time. Science takes time, and researchers are eagerly analyzing results of the mission to see how much more the body changes after a year in space. 1 year is a stepping stone to a 3-year journey to Mars, and Scott's data will help researchers determine whether the solutions they've been developing will be suitable for such a long, onerous journey. Beware, what you're about to read can be scary. But the good news is NASA has been working to solve these problems with some of the most brilliant minds in the field. Rest assured, when we take the next giant leap to Mars, we'll be ready. Gravity fields. There are 3 gravity fields you would experience on a Mars mission. On the 6-month trek between the planets, you would be weightless. On the surface of Mars, you would live and work in approximately 1/3 of Earth's gravity, and when you return home, you'll have to readapt to the gravity we take for granted. Transitioning from one gravity field to another is trickier than it sounds. It affects your spatial orientation, head-eye and hand-eye coordination, balance, locomotion, and you're likely to experience motion sickness. If you have to land a spacecraft on Mars, it could be a pretty dangerous situation. NASA has learned that without gravity working on your body, your bones lose minerals, with density dropping at over 1% per month. By comparison, the rate of bone loss for elderly men and women on Earth is 1% to 1.5% per year. Even after returning to Earth, your bone loss might not be corrected by rehabilitation, so you could be at greater risk of osteoporosis-related fractures later in life. If you don't exercise and eat properly, you'll lose muscle strength, endurance, and experience cardiovascular deconditioning since it does not take effort to float through space. The fluids in your body will shift upwards to your head, which could put pressure on your eyes, causing vision problems. You're apt to develop kidney stones due to dehydration and increased excretion of calcium from your bones. Medications react differently in your body in space. Nutrition, including eating enough, becomes important. Otherwise, you could compromise your health since nutrients are required for the function of every cell and system in your body. By analyzing how your body changes in weightlessness and after returning to Earth's gravity, protection against these changes for a Mars mission can be developed. Functional task testing is in place to help detect and minimize the effects of space on your balance and performance. Fine motor skills testing is done to detect any changes in your ability to interact with your computer-based devices. Distribution of the fluids in your body will be closely monitored to help evaluate any connection to changes in your vision. Compression cuffs worn on your thighs will help keep the blood in your lower extremities to counteract those vision changes. Your back pain would be monitored by obtaining spinal ultrasounds. You will perform periodic fitness self-evaluations that help researchers better understand the decline in cardiovascular function that can occur during spaceflight. Some medicines, like potassium citrate, may help you combat the physiological change that could increase the risk for developing kidney stones. Bisphosphonates drugs have shown to be effective in preventing bone loss. NASA has also designed an efficient way to collect and measure how much urine you produce in space, which is essential to human research since it reveals key information about your health. You'll get proper nutrition, including vitamin D supplements since you can't walk outside under the sun. And lastly, good old regular exercise has been shown to keep your heart healthy and your bones and muscles strong, your mind alert, your outlook more positive, and may even help with your balance and coordination. Isolation/confinement. NASA has learned that behavioral issues among groups of people crammed in a small space over a long time, no matter how well trained they are inevitable. Expedition crews selected for a stay aboard the space station are carefully chosen, trained, and supported to make sure they can work effectively as a team for 6 months. Crews for a Mars mission will undergo even more scrutiny and preparation since they will travel farther and longer than any previous human, being more isolated and confined than we can imagine. The types of problems you may encounter are a decline in mood, cognition, morale, and interpersonal interaction. You could also develop a sleep disorder because your circadian rhythm might be thrown off due to the 38 extra minutes each day on Mars, or by a small, noisy environment, or the stress of prolonged isolation and confinement. Depression could occur. Fatigue is inevitable given that there will be times with heavy workload and shifting schedules. Still, periods of monotony may lead to boredom rearing its ugly head. Misunderstandings and impaired communications with your team members might impact performance and mission success. A lack of fresh food and mean variety or deficiency in nutrition may further contribute to physiological and cognitive decrements. Also, far more autonomy will be required due to the very long communication delays over the vast distances from the space vehicle to Earth. And then there's the possibility of the third quarter effect, where morale and motivation decline 3/4 of the way into a mission, regardless of how long the mission lasts. The more confined and isolated humans are, the more likely they are to develop behavioral or cognitive conditions and psychiatric disorders. NASA has been studying people in isolated and confined environments for years and has developed methods and technologies to counteract possible problems. They're using clever devices like actigraphy that help you to assess and improve your sleep and alertness by recording how much you move and how much ambient light is around you. New lighting, spurred by the development of light-emitting diode (LED) technology, will soon be used on the space station to help you align your circadian rhythms, which will improve sleep, alertness, and performance. You can assess the effect of fatigue on your performance with a 5-minute self-test. Journals give you a safe place to vent your frustrations and give researchers a tool to study behavioral issues and other things that are on the minds of crew members who are living and working in isolation and confinement. All of these methods and technologies will help us prepare for longer, farther exploration missions. NASA has learned that the ecosystem inside the spacecraft plays a big role in everyday astronaut life. Microbes can change characteristics in space, and microorganisms that naturally live on your body are transferred more easily from person to person in closed habitats like the space station. Your stress hormone levels are elevated and your immune system is altered, which could lead to increased susceptibility to allergies or other illnesses and disease. Every inch and detail of your living and working quarters must be carefully thought out and designed. Just like you wouldn't want your house to be too hot, too cold, cramped and crowded, very loud, or not well lit, you wouldn't enjoy working and living in such a dwelling in space either. NASA is using technology to monitor the air quality of the space station to ensure the atmosphere is safe to breathe and not contaminated with gases like formaldehyde, ammonia, and carbon monoxide. Your urine and blood samples are analyzed to ensure the stress of spaceflight hasn't caused infectious illnesses like the Epstein-Barr virus to be reactivated, and the risk of microbes that may cause disease to you and your crew members will be evaluated using advanced molecular techniques. Various parts of your body and the space station are swabbed for analysis of the microbial population that inhabits the environment. Effective monitoring techniques are in place to identify how your immune system changes in space by analyzing blood, saliva, and urine samples. Your living quarters and work environment are carefully planned and evaluated to ensure that designs balance comfort and efficiency. And the lighting will be similar to what you experience naturally on Earth thanks to the new LED lighting system. Space radiation. The most dangerous aspect of traveling to Mars is space radiation. On the space station, astronauts receive over 10 times the radiation than what's naturally occurring on Earth. Our planet's magnetic field and atmosphere protect us from harsh cosmic radiation. But without that, you're more exposed to the treacherous radiation. Above Earth's protective shielding, radiation exposure may increase your cancer risk. It can damage your central nervous system with both acute effects and later consequences, manifesting itself as altered cognitive function, reduced motor function, and behavioral changes. Space radiation can also cause radiation sickness that results in nausea, vomiting, anorexia, and fatigue. You could develop degenerative tissue diseases such as cataracts, cardiac, and circulatory diseases. The food you eat and the medicine you take must be safe and retain their nutrient and pharmaceutical value, even while being bombarded with space radiation. A vehicle traveling to Mars and a habitat on Mars will need significant protective shielding, which is nonetheless futile against some types of space radiation. The space station sits just within the Earth's protective magnetic field, so while our astronauts are exposed to 10 times higher the radiation than on Earth, it's still much less than the radiation a mission to Mars will encounter, and of a different type. Shielding, monitoring, and operational procedures control the radiation risks to accepted levels to keep you safe. To learn what happens above a low Earth orbit, NASA has extensively used ground research facilities to study how radiation affects biological systems, and more importantly, how to protect them. They are developing unique ways to monitor and measure how radiation affects you while living in space and to identify biological countermeasures. Finally, methods to optimize shielding are being studied to help protect us on a journey to Mars. Distance from Earth. Planning and self-sufficiency are key. How far away is Mars? 140 million miles from Earth on average. In contrast, the Moon is only 0.239 million miles away. With a communication delay of up to 20 minutes one way while on Mars and the possibility of equipment failure, you must be able to complete the mission on your own. And what type of food and medicine would you pack if you had to go on a 3-year trip without access to a grocery store or pharmacy? Hopefully you plan correctly. NASA is using the space station to figure out what types of medical events happen in space over 6 months and what type of skills, procedures, equipment, and medication are needed. So you'll have a good idea of what you'll need to pack for Mars. You can produce intravenous solution from purified space station cabin water and then mix it with salt crystals to produce normal saline for medical administration. Even if you aren't a doctor, you and your crewmates would perform ultrasound scans of yourself using training you received before flight to monitor your bone and organ health. NASA is studying and improving food formulation, processing, packaging, and preservation systems to ensure the nutrients remain stable and the food remains acceptable. Space-resilient medications and packaging that preserve the integrity of pharmaceuticals for long-duration missions have also been developed.